Now that we've introduced the math that's required for this course, we're ready to proceed to the first major topic in physics, kinematics, the description of how things move. Motion means a change in position, and so we need a system of measuring the positions of objects. A coordinate system, like a number line, will work just fine. Here's a number line. We notice it stretches horizontally along the x-axis. I've marked the origin. A number line does a few things. First, it gives every point on the line a distance from the origin, 1 meter, 2 meters, 3 meters, and so forth. Second, you'll notice that with respect to the origin, there are two directions, left and right. And this is represented in the numbers too. Everything left of the origin is negative, while everything right is positive. So we can use negative and positive numbers as symbolic representations of the left and right directions respectively. That means that every position on the number line can be distinctly and unambiguously represented with two pieces of information: its distance from the origin and the direction, left or right, that it lies with respect to the origin. That means every position can be represented as a vector. Now, before we go on, there's nothing sacred about having left be negative and right be positive. It's a matter of convention, and in fact, we will sometimes use right as negative and left as positive. But for the moment, we'll stick with that convention. Let's explore position in a more tangible sense. If I place this car at the origin, I can say its location is 0 I hat meters. Its distance from the origin is 0, and all our distances are being measured along the x-axis, hence I hat. If the car were placed here, we would say its position is 2 I hat meters. 2 meters from the origin along the x-axis and in the positive direction, that is right. Hence, the position is positive. And over here, the car's position is negative 3 I hat meters. 3 meters left of the origin along the x-axis. So this coordinate system gives us an unambiguous way of locating the car, and it uses vectors to do so. But usually in physics, we're not too concerned about the absolute position of an object. We're more interested in how something has moved, how its position has changed. Now, if you wanted evidence that an object had changed its position, here's one way to do it. Take a photo of the object. Then take another photo after a period of time has elapsed. Then compare the positions of the object in the two photos. We can describe a difference in the positions using a quantity called displacement. The symbol for displacement is this. That triangle out front is the capital Greek letter delta. We call the symbol for displacement delta x. You'll notice it's a vector. Displacement is calculated like this. Take the final position of the object and subtract the initial position. In this case, the final position is 3 I hat meters, and the initial is 0 I hat meters. So the displacement is 3 I hat meters. What if we took a photo of the object in this position, 3 I hat meters, and later took a photo of it at this position, negative 2 I hat meters? Again, we would calculate its displacement as final minus initial. That's negative 2 I hat meters minus 3 I hat meters, or negative 5 I hat meters. The direction of displacement is given by its sign. A positive displacement means an object has moved in the positive direction, in this case rightwards. A negative sign means the object has moved in the negative direction, that is, leftwards. Now, suppose we were to ignore the direction of displacement and only focus on its size. That means we would lose the I hat, but we would also lose the negative sign, since that is what indicated direction. We have now created a scalar version of displacement. It is called distance. Unlike displacement, distance has no direction as it is always positive. Here's an example of the difference between displacement and distance. Suppose you run on a 400-meter track and you end up where you started from. Because you ended where you started, your position has not changed between the two photographs, so your displacement is 0. Your final position and initial position are the same, and this could only occur because you reversed your direction of motion midway through the run. So part of your run was in the negative direction while the other part was in the positive direction. But since distance doesn't account for direction and cannot be negative, the distance that you have run is 400 meters. So the displacement is 0, but the distance was 400 meters. We don't really use distance too often in physics. Since displacement is a vector, it is more useful and more commonly seen. In our earlier example, we took 2 photos of the car, one when it was at 0 I hat meters and one where it was at 3 I hat meters. Some time clearly elapsed between those photos. Let's say it was 2 seconds. Then we would be able to say how quickly the car moved. How quickly or slowly an object moves is simply a measure of the time required for it to change its position. Or equivalently, it is the rate of change of position. In kinematics, the term for rate of change of position is velocity. There are 2 types of velocity, and we will look at both. Suppose you take the displacement of an object across 2 photos and divide it by the time that elapses between the 2 photos. We could symbolize that as either displacement over time, or equivalently, final position minus initial position over time. This calculation yields a type of velocity called average velocity. Average velocity is easy to calculate. Since the car traveled 3 I hat meters in 2 seconds, its velocity is 1.5 I hat meters per second. On the other hand, if the car traveled from a position of 3 I hat meters to negative 2 I hat meters in 8 seconds, we could calculate its velocity as negative 0.625 I hat meters per second. Just like with displacement, a positive velocity means the object is moving in the positive direction, while a negative velocity means it is moving in the negative direction. There is a scalar version of velocity, that is, velocity without the sign or any direction. We call this quantity speed, but again, kinematics mostly uses vectors, so we won't be seeing speed too much. Now, in reality, this measure of average velocity is an oversimplification. When you drive, it is very unlikely you will travel at a constant velocity, even with the cruise control on. If you look at your speedometer, you will see it fluctuates even over pretty short times. The speedometer displays those small fluctuations that would be smoothed over by average velocity. So we say the speedometer reads your instantaneous velocity. In kinematics, we use instantaneous velocity more often than average velocity. We've now defined velocity as the rate of change of position, but we can go one step further by defining the rate of change of velocity. That would be how quickly the velocity of an object increases or decreases. For instance, if you're driving on Route 9 at 40 miles an hour and you ease on the gas pedal, your velocity would gradually increase to 41, then 42, then 43, and so forth. But if you floored the gas pedal, your velocity would leap up to 45, 50, 55, your velocity changes more quickly in the latter case. The rate of change of velocity is called acceleration. We can calculate it like this. Take a photo of the speedometer in your car. Then, after some time has elapsed, take a second photo. Take the difference in the two velocities, v final minus v initial, and divide by time. That's acceleration. If you start at 0 meters a second and you ease on the gas pedal, you might get to 40 I hat meters per second in 20 seconds. Your acceleration would be 40 I hat meters per second minus 0 I hat meters per second, all divided by 20 seconds, which works out to 2 I hat meters per second squared. As we can see, acceleration, just like displacement and velocity, is a vector. Its units are meters per second squared. By contrast, if you start at rest and floor your gas pedal, you might reach 40 I hat meters per second in only 7 seconds. In this case, your acceleration is 40 minus 0 over 7, or 5.71 I hat meters per second squared. That's a much greater acceleration. Finding the size of acceleration is no problem, but the direction is a different matter. We saw earlier that a positive displacement or a positive velocity means an object is moving in the positive direction. But for acceleration, it's not so simple. Suppose you're driving at 40 I hat meters per second and you slow down to 0 I hat meters per second because the traffic is bad. It takes you 7 seconds to do so. What is your acceleration then? It is final velocity, 0 I hat meters per second, minus initial velocity, 40 I hat meters per second, all over 7 seconds. That works out to negative 5.71 I hat meters per second squared. Negative. But this whole time you were driving in the positive direction. Unlike velocity and displacement, the direction of acceleration doesn't always match which way you're driving. You can indeed have a negative acceleration even if you travel in the positive direction. Specifically, acceleration is negative if you slow down in the positive direction. You might now be wondering what would happen if you traveled in the negative direction. Let's try. Here, we are starting at 0 I hat meters per second, and we are eventually reaching a velocity of negative 40 I hat meters per second. It takes 20 seconds to do so. So when we calculate the acceleration, we get negative 40 I hat over 20 meters per second squared, or negative 2 I hat meters per second squared. So when we're speeding up in the negative direction, acceleration is also negative. Finally, what happens if you start at negative 40 I hat meters per second, but 20 seconds later you reach 0 I hat meters per second? When you calculate it out, the acceleration is positive 2 I hat meters per second squared. We can summarize all these findings in a table. To keep it simple, we can say if you speed up in the positive direction or slow down in the negative direction, your acceleration is positive. Vice versa, if you slow down in the positive direction or speed up in the negative direction, your acceleration is negative. At this point, we have defined 3 major variables that we can use to describe the motion of an object. Displacement, the change in position with direction. Velocity, the rate of change of position with direction. And acceleration, the rate of change of velocity with direction. In principle, we could look at the rate of change of acceleration and keep going. But what we'll find is that a lot of physics problems do not require any further variables. In the next video, we will see how to use these 3 quantities to describe a wide range of physical systems.